Welcome to the second energy assignment for the grade 11 physics course. I've tried to again restructure the assignments so they give you a little bit more help and tie in with the videos as we go, so you have a little less swapping to do. And as usual, there's a miniature lesson here. You can still go find my full lessons elsewhere, but the idea is to try to encapsulate it here. I flagged the questions for you. If they're yellow, you gotta be able to do that. You really must for grade 11 and lead you on to grade 12. If they're blue, then that's real excellence. And if you're doing a red one, then you've gone beyond the course, you're into grade 12 territory. So I'm again letting you pick your own personal best. The mark value drops. So you'll see the most difficult questions are worth the least number of marks. And I've discussed this before. The problem when we give you grades based on the procedure, then the most difficult questions wind up counting for the most marks. And I want you to get 70% easily. I would like 85% to be well within your reach. But once you climb beyond that, it should be getting harder and harder and harder. So I've staged the questions very carefully to make it tougher to reach that perfection level. These are all the possible formulas for work that will lead you right into university. I would like you to become familiar not only with EI and EF, but E and E primed. It's just a change in terminology, who cares? Conservation of energy simply states that the energy we start any problem with is the energy we end any problem with. Work equals force times distance converts to all of these. I've shown you 2 proofs on the website, but you don't need to memorize them. But you won't be doing anything beyond this in high school. The most common type of conversion is to kinetic to potential, and there's a reason there's a Canada's Wonderland Day for physics when we're not confined because of the plague. The conversion of energy due to position on a roller coaster to energy velocity is conversions. So you must know the roller coaster problems cold. The most common conversion is to take energy of height, potential energy is mgh, and equate it to kinetic, 1/2 mv squared. The roller coaster can either have total potential, total kinetic, or a mix. But in all cases, the total energy at position 1, 2, and 3 are equal. My video goes into that in detail. Because the mass occurs in both of these formulas, in most energy conservation problems, you can cancel out the mass. Not if I ask you to calculate one of the energies for me. If I say, what is the total kinetic energy, then you must have the mass. But if the two are going to be equal, the mass is going to cancel. And get used to simplifying that way. It saves you a lot of work, because I could be mean and say, I'm going to give you the mass of 9.11 times 10 to the minus 31 kilograms, which is the mass of the electron. Okay? So I've drawn it to your attention. This is the critical problem. The stuff that is not in the course. It's there. It's done. I think I do it more than other teachers do. But really, heat and combustion, then we get some actual power. So the videos on heat, you can see the 2 links there, and combustion. I would really encourage you to go through the heat and combustion ones because and watch the videos on that, because this will allow you to start, becoming the rocket scientist, where we start bringing in the physics of heat and the chemistry of combustion combined, so we can start doing some really cool calculations. Elastic energy is strictly grade 12. If you handle the elastic energy problem, you have done grade 12 physics. We will touch on electrical maybe at the end of the week, and nuclear, if you want to, I can show you a simple Einstein's equation. So when we go through these questions here, if they've been flagged yellow, you really want to know how to do those for grade 12. On the 2 baseball ones, I've actually set up 3 videos for you to watch. And you can read, like, some scientists did analysis of what happens when a person was killed with a baseball bat. You can read the abstract. It's macabre, but it's also fascinating how they got that. And this is where I got the values that will kill you on a strike to the head. So they've measured what it takes to actually beat a person to death. And this gets used in court cases when they try to explain, was it an accident or not. So I want you to watch the videos and do your best guess to just estimate how far the pitcher swung his arm and how far the people move their mitt back when they catch. Doesn't matter if you're right or wrong. You're just guessing from the video, but you get a real world distance. It's going to work. I'm marking you on your ability to manipulate the equations, not read data off the screen. So do not get a ruler and put it to the screen. Just take a guess. Oh, his arm traveled a meter. Oh, his glove kicked back 30 centimeters. Do not try to measure it off the screen. The King Dakar roller coaster is the tallest in the world. The tower is 139 meters high, and this hill is 39 meters high. So I want you to watch the video. If you click on the website, they have a film clip of the ride on that roller coaster, and that will really give you a feel for what I'm asking you in the question. And so this roller coaster, unlike many others, starts on the ground, and they basically rocket power you up the first hill. So there's a little bit of a change. Watch the video and you'll understand. Question 5, so you understand this one. There's an old thing, if you drop the penny off the top of the CN Tower, it would kill a person. Or they'd say it'd go 8 centimeters into their skull or whatever. And it's just like, what's a penny? You guys are probably asking. So what I want to know is, if you picked up a bullet, you just took like the tip of a bullet and you dropped it off the top of the CN Tower, would the bullet ever reach the actual speed like it came out of a gun? All right, so how fast is it going to be going from the top of the CN Tower? And compare that to the speed of a bullet. And just look up muzzle velocity of a bullet. And pick a value and go, well, I found this on the internet. And when I calculated dropping a mass off the CN Tower, do you do it from the observation deck or the tip? I don't care. Pick one of the heights, look it up. Now, the force of friction problem is... we're going to take force of friction, going back to Newton's law, and you're just going to calculate the work done against friction when pyramid builders drag a stone of mass 25,000 kilograms, a distance of 5 meters, on a surface of mu 0.337. So go back and look up your force of friction stuff. It's a good review. Now, the blue question here, what if we're tugging on an angle? You already did your trigonometry for forces on an angle. So the same thing here. You're going to compute a horizontal force and then work out the acceleration. Now, here's the question. Do you need a mass for this problem or not? And if you think you need a mass, make one up. Okay? Use your intelligence. See if I omitted something that you need for that question. And then 8 and 9 are the same question, really. Just one is trickier in its phrasing. Oh, there's a grade 12 question, number 10. And number 11, I flagged it as blue because you had to do number 10 to do number 11. And number 12 is also, it is grade 11. It's like the heat energy ones used to be in the grade 10 curriculum. So you can do them if you give them a try. And remember, I'm sitting at home just doing terrible things to my cat with a fork while I'm waiting for you guys to ask me questions. So this assignment, I've tried to make it a little bit more in line with the videos directly, and it gives you some little sort of like at least video experiments to tie this together. Okay, so again, I'm still here anytime you want my help.